Hello, ladies and gentlemen. I am going to go through the reaction rate law notes with you. I just want to make sure we're understanding this, and hopefully this will help you if you're not getting it from the help sessions or the other video that I posted. A rate law is an equation that expresses the mathematical relationship between the rate of a chemical reaction and the concentration of the reactants. If this reaction is a one-step reaction, the reaction that we're looking at here, A turning into B, then the rate expression would be rate equals K times the concentration of A, where K is some sort of specific rate constant. Okay, that is something that you're calculating in your problems. This is a numerical value that relates the reaction rate and concentration of the reactants at a given temperature. The larger the value of K at a given temperature, the faster the reaction is going to occur. The reaction order defines how the rate is affected by the concentration of that reactant. So for the rate law that we saw before, rate equals K times the concentration of A, the order in the rate expression, let's see. The exponent in the rate expression is known as the rate order for that reaction. This reaction would be called first order with respect to A because it's understood that A is the same thing as A to the first power. A first order reaction means that the rate changes in the same proportion that the concentration changes. So when A quadruples, the rate would also quadruple. It would have the same effect there. If we were looking at other reaction orders, and this was our generic reaction here, the question is saying, would the exponents m and n be the same as coefficients a and b? And the answer is no. The only way you can figure out what these values are, what m and n are, is through experimental data. So the only way you can figure out the order of a reaction is through experimental data. So a big part of our problem that we're going to be doing with these calculations is figuring out the orders of the reaction. Is it first order, or second order, or third order, or zero order? So when you have a first order reaction, what that means is that when A doubles, your rate's going to double too. It'd be like saying, okay, we doubled it, so we have 2 to the first power. Well, 2 to the first power is 2. That's why when the rate doubles, or when the concentration of A doubles, the rate doubles as well. For a second order reaction, when A doubles, your rate is going to quadruple. It'd be like saying 2 to the second power is 4. We doubled our rate, and that doubling to the second power is equal to 4. So that's why it's quadruple. If we have a third order reaction, when A doubles, rate is going to be 8 times bigger. 2 to the third power is equal to 8. So that's why it is 8 times bigger. And if I have something to the zero order, if I doubled A and I brought that to the zero order, that's going to equal 1. Anything to the zero power is equivalent to 1. So that means your rate stays the same. It has no effect on changing the rate. So because of that, zero order do not include zero order in your rate law expressions. So we're going to look at another sample problem here. We did, I did a couple for you in the other video, but we're going to look at this one in our notes as well. So hopefully it'll start making a little bit more sense for some of you. So when the concentration of A doubles here, the only time that we can look at A is when B is constant. B is constant in trials 1 and 2. So we're going to look at the concentration of A in trials 1 and 2. Notice how it doubles. It goes from 0.1 to 0.2 there. When it doubles, the rate also doubles. And because that rate also doubles, that is meaning it is going to be a first order with respect to A there. Now, if we look at B, the only time we can look at B now is when A is constant. A is constant during trials 2 and 3. Notice that as B doubles, our rate quadruples there. And because it quadruples when the rate was doubled, that means we have a second order with respect to B. So how can we figure this stuff out mathematically? If I'm going to look at doing A, it's going to be pretty much the same idea as I said before. We have to make sure that B is held constant, and then we're going to divide the concentration of A, but we're going to take trial 2 divided by trial 1. So we're taking a bigger number divided by a smaller number. That way we're not working with fractions. And we bring that to some power, and that's going to equal our rates from trial 2 divided by trial 1. So 0.2 divided by 0.1 is 2.00 to some x power, and that's going to equal the 4 divided by 2, which comes out to also be 2.00. So x must equal 1. 2 to the first power equals 2, which is what we saw when we did not do it mathematically. We saw when the rate doubled, the concentration doubled, and we had a first order there as well. Now, if we do the same thing with B here. So with B, we said we're going to look at trials 3 and 2 and what those rates are. So when B doubles, goes from 0.2 from 0.1 to some x power, and the rate of trial 3 was 16.0 times 10 to the negative third, divided by the rate of trial 2, 4.00 times 10 to the negative third. That there comes out to be 2.00 to some x power equals 4.00. So 2 to the second power is equal to 4. Now, when we write our rate law expression, they always start the same way. Rate equals K. That will be the same every single time. And then you're going to multiply it by the concentration of your reactants. Our reactant A was to the first power, and our reactant B was to the second power. We saw it coming to the second order there. Sorry. So that would be our rate law expression there that you should be looking at. Now, next question it says is calculate the specific rate constant for this problem. Specific rate constant is K. That's what I'm calculating here. I'm finding K. To calculate the specific rate constant, then I need to isolate it and get it by itself. And I do that by dividing by A to the first and B to the second. So it ends up being rate divided by A to the first power and B to the second power. And then to calculate K, I'm going to plug in the numbers from trial 1. So I'm going to use trial 1 data in these spots here. So my rate for trial 1 was 2.00 times 10 negative third, and my concentration for A was 0.100, and my concentration for B was 0.100. So rate is 2.00 times 10 to the negative third molar per second. That's a bad molar. And A was 0.100 molar to the first power. And B was also 0.100 molar to the second power. Since it's 0.100 and 0.100 squared, really I'm dividing it by 0.100 to the third power. Solve for that first, and then take 2.00 times 10 negative third divided by that answer. When you do that, that has 3 sig figs in the answer, so it'd be 2.00. And then we have to come up with your unit. In this problem, what you're really doing is taking, or you have a molarity per second, and you are dividing that by molarity cubed. Well, it's the same as multiplying it by its reciprocal. So molarity per second times 1 over m cubed. Simplifying that, this m cancels and becomes a 1, and this now becomes a 2. So what I have left is a 1 over s times m squared for my unit there. That would end up being my specific rate constant value and unit. The sum of the orders in the rate law expression is your overall reaction orders. So really it's the sum of your exponents or your orders. In this problem here, it's an exponent of 1 and 2. So if you add those up, it would be a third order reaction overall. Come on.